To recap from the earlier video, the synchronization plane is critical to the operation of any 5G network. Here's why it is critical. 5G users have high expectations. They want fast and they want reliable. Basic 5G requires accurate time synchronization just to work. The really high performance comes with enhanced radio techniques that require even tighter synchronization. To achieve that level of synchronization performance, every piece of equipment in the chain needs to meet exacting performance requirements. Network architects will demand devices that conform and that can be demonstrated to conform. If the devices don't work, the network won't work and everyone loses. There are two very different types of timing requirements that are important in a 5G network. Let's look at time and frequency synchronization first. Time synchronization is a measure of how well the clocks on two separate pieces of equipment are aligned. If the clock here on this radio unit is at 12 noon, and the clock on this radio unit is at 12 noon, then they are perfectly aligned. The time alignment error is 0 seconds. If the clock here on this radio unit is at 12 noon, and the clock on this radio unit is at 12 noon and 3 seconds, then the time alignment error is at 3 seconds. Simple. This is where the requirements start. If these two radio units are near to each other or in adjacent cells, then the radio transmissions must be time aligned or they may interfere with each other, or a handover from one to the other may fail. The third generation partnership project, 3GPP, has defined a basic requirement that there are no more than 3 microseconds of time alignment error between two such radio units. Many other device and network timing requirements derive from this starting point. Let's look at the practicalities of maintaining that level of time alignment error. The components that are typically used to implement a clock on such radio units are not capable of maintaining such accuracy over a long term. In practice, each clock is connected to a very accurate reference source and is corrected periodically to maintain alignment with that reference source. Now, if each clock is maintained to within plus or minus 1.5 microseconds of a common reference, then they will be within 3 microseconds of each other. This creates our next requirements. So let's drill down into it a little bit. Highlighted here, you can see that the connection between the ORU clock and the reference clock passes through multiple interim devices. Each of those devices will add some time error as the reference passes through. So the plus or minus 1.5 microsecond allowed will be an accumulation of the time error of all the devices in the chain, including the ORU itself. The ITU have defined types and classes of equipment that are used in such networks and allocated a portion of this 1.5 microseconds to each. So now we have 3GPP requirements, remember the 3 microseconds, and ITUT requirements to meet. To support the open nature of ORAN, the ORAN working groups have defined performance characteristics of the ODU and the ORU so that the equipment from different manufacturers can interoperate with each other. They have gone one step further and defined methods to test conformance to those requirements. Putting all that together, you have a comprehensive suite of performance requirements from the ITU and 3GPP, referencing IEEE 1588 PTP, the protocol used to synchronize the ORU with the reference source, through the ORAN CUS specification, to the ORAN conformance test specification. That is a lot of documentation and a lot of requirements. The key takeaway is that the synchronization requirements for 5G and for ORAN are multifaceted and layered. If you leave out an important piece, the system will fail. That will probably leave you wondering, who is responsible for testing what? The short answer is everyone has a part to play. Certainly, the buck stops with the network operators. After all, it's their network, and they have to make sure it works and that it remains working. However, the networks are built with network elements from third parties, not just the RUs, DUs, and CUs, but also any switches and routers in between. They must be tested to demonstrate compliance to the required standards. The network architects will rightly demand that. It will be important to ensure that what they are demonstrating is aligned to what is expected, both in terms of performance and test methods. The testing labs often play an important role in aligning those expectations and methods. The network equipment manufacturers use components from the chip manufacturers, who therefore must demonstrate the performance of their devices. Their testing should likewise be aligned with the network equipment manufacturers, so they're all validating the same way and results and performance match. System integrators can often be validating at chip level, equipment level, and network level. In the next session, we will dive into what needs to be tested and how.